George is building a rectangular container out of metal, no top, to store some garden supplies. Fixed surface area of 100 square feet, maximize the volume. He wants the length to be twice the width. Okay, so we can draw a picture of this, which will be helpful. The base should be, the length should be twice the width. So rectangular, something like that. If I call the width x or w, this would be 2x, and we'll call this y. That's the height. Okay. So these go, we have a function we want to, the primary equation we want to maximize, we want to do the calculus on. That's the volume equation. The volume of this thing would be this times this times this, right? The product of the three dimensions. So 2x times y. Okay, so what's the surface area? Well, the question would be, now you got the base, all right, you got this guy, the base would be 2x squared, so surface area is 2x squared plus, let's see, how many of these do we have? There should be two of those, and that's given by 2xy, so plus 2xy. And then there should be two of these, right? Should be two of those, one here and one in the back. So that should be 2 times xy. All right, so that gives you a 2x squared plus 6xy for the surface area. George has a fixed, and that's 150 feet. All right, so if you get that far, then the idea is to solve this for one of your variables. We need this volume equation to be a function of one variable, right? So and then we could take the derivative, set it to 0, and solve. So I can solve this for y, so I will subtract the 2x squared, and then I'll divide by the 6x, and that's y, and then I can take, well, I can take half of those. So that would be 75 minus x squared over 3x is probably the best way to write that. Factor out of 2, and cancel those out. So then this goes here. So now my volume is simply a function of x, 2x squared times 75 minus x squared, all divided by 3x. One of those cancels out with that. So I'll have a 2/3, factor out the 3, and then I'll run the x through. See how this looks, 75x minus x cubed. And that's probably the best looking. Yeah, you could just run the 2 through and just, have 150 minus 2x cubed, both of those over 3. Doesn't matter. It's kind of a preference thing before you do the calculus. I'll leave it like this and then take the derivative, constant multiple rule, 75 minus 3x squared. And then we take this and set it to 0. Okay, so when I set that to 0, I'm just looking at this guy. When does that equal 0? So that would be 3x squared equals 75. Divide by 3, and we get a nice integer answer. Square root of 25 plus or minus, but in this case, we only have to worry about the plus. So that gives me my value for x that should maximize the volume. X should be 5, okay? Which makes this 10. And then what should y be? Well, we can come back to, where is it? This equation. And we can solve for y. And that should be, I'll just save a little bit of time. It should be 10 over 3 is what you should get. So those are your dimensions, and those should be in feet. 10 foot by 5 foot by 3 1/3 foot will maximize your dimension. There's one more thing we should do. We should make sure that that is indeed a maximum. So I got a little more space over here, right? Because we don't really know it's a maximum. We just know that's when the first derivative equals 0. So how do we know it's a maximum? We got to do the first derivative test or the second derivative test, which I think should be a little bit easier. So let's see how that works. Second derivative test. there's the second derivative. And if you remember the second derivative test, you take your critical number, right? This, where'd it go? X equals 5 is a critical number. Take your critical number and you plug it into the second derivative. We know it's the graph should be leveling off there, but we're not sure if it's leveling off like this as a minimum or leveling off like this as a max, which is what we're hoping for. So we got to verify that. Okay, so we know it levels off, but which one is it? Or it could, I guess, be that as well. All right, so which of the three is it? Well, this should tell us. Okay, so what we have here is 2/3 times I think that shouldn't be there. I know I was missing something, right? The first derivative was 75, not 75x. When you take the second derivative, it should be 2/3 times negative 6x, right? Because the derivative of 75 is 0. So that makes more sense to me now. 2/3 times negative 30, whatever that is, negative 20, doesn't matter. What really matters is that it's negative, okay? So that indeed tells us that it's concave down there. So we have this scenario, concave down, which means we have a maximum. So it just verifies that a maximum occurs here at x equals 5.